Hey, Tanaya, can you hear me?
Yes, wait, hold up. I need to get my headphones connected. They're not
Okay,
connecting.
okay. Yeah. Take your time.
All right, hello?
Hello, hello. Can you hear me?
Okay, yeah, it's working.
That's good. That's good. How's what 118A going for you so far this quarter?
Um, I mean, I feel like because I'm taking a big course workload, it kind of is difficult to
Mm,
handle. I mean, this weekend, because I did make a plan for how I can stay consistent, because I've noticed I've been like spending one day on physics, next day on OChem, and it's kind of bad doing that. So,
Physics and Ochem at the same time. That's difficult for sure. Like, are you taking the 7 series or the 9 series?
yeah,
I
I'm
think you're
doing
taking
the
the
nine
the
series.
9 series. Yes, yes, yes.
Yeah,
Um,
I'm also doing math and eng, so it adds up.
oh, that's 4 STEM classes in 1 quarter.
Mm-hmm.
Oh my gosh. Are you second year, third year?
Second year.
Second year. I see. Okay, okay. Oh yeah, thank you for creating that like polishing up the Discord server for me. Yeah, because I
Yeah,
didn't.
no problem. Thank you.
Yeah, yeah, of course, of course. What was quiz one today about?
It was about acids and bases. It
Mm,
had some stuff about drawing structures in it, and that's what
mm,
my discussion quiz yesterday was about.
yeah.
Um, I have her syllabus if you want me to send that to you.
Leave-in
Like
syllabus.
of all the, yeah, of each lecture, like what's the topic.
Yeah, yeah, that'd be great. You could send it on Discord. That'd be great. Yeah.
Okay.
Thank you. Do you also go to the ATC or nah? You just
No, I mean, I used to try to go for Gen Chem, but I didn't get too much help from there,
okay,
so I
okay.
stopped going.
Yeah, I see. Makes sense. Mhm. Yeah, because today we could go over acid base problems, pKa, solving effects, nomenclature, and Newman projections.
Okay, yeah, I think I'll go over a little bit of next lectures too.
Okay, that's good. Yeah. Yeah. Let's see. Okay. So let me share my screen here. Okay. Okay. So we could go over like acids and bases right away. Like how to determine what's the stronger acid, what's the stronger base, without knowing the pKa. But first, are you familiar with how to like compare acids using the pKa values?
I might need a refresh on that.
Yeah, yeah, of course. So let me go over what Ka values are first, right? So just as a general thing, let's say we have H attached to A, and A is just some kind of random molecule, and that's gonna be the acid,
Mhm.
right? Like it could be
Okay.
H3O plus, HCl, HBr, any acid, right? And let's say we have a base like water, right? And this is going to be an equilibrium where if water takes a proton from HA, that's going to become hydronium ion, H3O plus. And then HA is going to become A minus. So there is like a flow to this, right? And I'm going to show you that right here. Oxygen has 2 pairs of electrons, one there and another here, because it's neutral. And for oxygen to be neutral, it has to have 2 bonds and 2 lone pairs of electrons, right? It has 2 bonds to hydrogen and it has 2 pairs of electrons. That's why it's neutral. Are you familiar with curved arrows and like what that represents in organic chemistry?
No, no.
Yeah, it's okay. So curved arrows, right? Like this right here represents the movement or the flow of 2 electrons, right? And where the arrow starts, which is this one right here, shows that it's starting from 2 electrons, either from a lone pair of electrons or a covalent bond. And then where it goes to is where the electrons are going to. And then in organic chemistry, we call that attacking, right? It's gonna attack something, right? So let's say this A here is bromine, right? What atom is more electronegative, bromine or hydrogen? Based on
I
the
would say bromine.
periodic table, bromine is more electronegative. So that means bromine is going to withdraw or pull electrons from hydrogen because bromine is more electronegative than hydrogen, right? And what charge are electrons associated with? Positive charge or negative charge?
Negative.
Negative charge, right? So because bromine is pulling electrons from the hydrogen, would you say bromine is going to be partial positive or partial negative?
I think it'd be partial negative, but like in chem, like sometimes like with acids and bases they use the like you're told that think of H as a positive.
Mm-hmm. H is a positive, correct?
Yeah.
Right. Because in chemistry, like you said, the acidic H is a positive. That's because it's attached to an electronegative atom, like bromine or oxygen or nitrogen, something like that. That more electronegative atom is pulling electrons from the H, and that because the H is losing electrons, it's becoming more positive.
Okay, yeah, that makes sense.
Uh-huh. Right.
That makes
And
sense.
are you familiar with the terms nucleophile and electrophile?
Yeah, we went over that in the last lecture.
Okay, okay. So can you describe to me what that is? It's okay if you don't know, if you forgot. I could go over it if you forgot. But can you tell me what you think they are?
So for nucleophile, I think that like, oh, it loves the nucleus. So it
Mm-hmm.
wants to build it. So it wants to attract protons. And then for electrophile, I think that it loves electrons. So it wants to take electrons from other molecules or atoms.
Yes, yes. And that's correct. And you know how opposite charges attract? Like
Yes.
positive charges attract negative charges? Because we know the
Yeah.
nucleus is overall positively charged, what charge would the nucleophile have to be to attract that positive charge?
It would have to start negative.
Yeah, it would have to be negative. So all nucleophiles are gonna have a negative charge character to it, like either a partial negative charge or a full negative charge. Right? Now,
Okay.
electrons are negatively charged, so that means the electrophiles would have to be positively charged to attract the electrons, the negative charge electrons like that. Right?
Okay.
Okay. So now, based on this right here, what partial charge does oxygen have on this H2O over here?
It would have a slightly negative one.
Yeah, and that's because it's more electronegative than the hydrogens are. So it's gonna pull electrons from the hydrogen, making it slightly negative. And it has 2 pairs of electrons here, one here and another one there. I'm
Okay.
gonna show you that one of the pairs of electrons on the oxygen is going to go and grab that hydrogen right there. Right? This oxygen here that's negatively charged is attracted to this positively charged hydrogen. Does that make sense? Like why like that oxygen is attracted to that positively charged hydrogen?
Yeah.
Because opposite charges attract, right? So when this oxygen is grabbing this hydrogen right here, we're gonna form a bond between this oxygen and hydrogen right there. Right? So that means that we're gonna break this bond, right? Because think of it as this oxygen is gonna take this hydrogen away from this atom, right?
Okay.
So how many electrons
Would
are in
the um would the oxygen have to be more electronegative than the atom?
Yes, that's a good point. So oxygen would have to be more electronegative than whatever atom this is to make this reaction favorable and go forward, right? If oxygen
Okay.
is less electronegative than whatever this atom is, right? Um, then then it's not gonna be favorable. It's not gonna happen as much, right?
Okay.
Right. Uh-huh. So now, how many electrons are in this bond right here?
2.
2 electrons, right? So when this oxygen makes a bond with that hydrogen right there, we're gonna break this bond and move those 2 electrons onto that atom right there,
Okay.
right? And you know how it's neutral to start with? Like this atom here is neutral. There's no formal charge attached to it. Like it has a formal charge of 0. It's neutral. What
Yeah.
charge do you think this atom will have if it gains 2 electrons?
-2.
Mhm. Oh, so it starts with 0. Whenever an atom gains a pair of electrons, right? 2 electrons, it's going to be -1 charge,
Okay.
right?
Okay.
Uh-huh. And I could go over how to determine formal charges with you because there's you know how there's a formula to it, like calculating formal charges
Yeah.
in Gen Chem. Yeah, I could go over that with you as well. Now if something gains a hydrogen bond, right? Think of it as adding +1 charge, right? So because this oxygen right here we see is neutral, it has a formal charge of 0, and it's making a bond with this hydrogen right here. 0 plus 1 is +1, right? So that's why we see here this atom that lost the hydrogen, it gained a pair of electrons from the bond. That's why it's negatively charged. This oxygen right here that is positively charged has 3 bonds, 1, 2, 3, and 1 pair of electrons, right? Before it had 2 pairs of electrons, but it used one of its pairs of electrons, which if I highlight in yellow right there, it's gonna be the electrons of that bond right there, which grabbed this hydrogen, which I'm gonna highlight in pink, which is this pink hydrogen right there. That's where the movement happens, right? I could also highlight this bond right here green, which is gonna be those 2 electrons right there that I highlighted in green, right? These 2 electrons here came from this bond right here. And we see that the arrow starts from the bond going to the atom, which is why we see the 2 electrons there. Those are the 2 new electrons right there. Right, any questions on that?
No questions.
No questions. Okay. Okay. So now, you want me to review on how to calculate formal charges with you? Because that is very important, like moving forward before we move on to any mechanisms and reactions.
Yeah, please.
Okay. Okay. So let's start with oxygen, right? Let's say we have H2O right here. And if you look on the periodic table, oxygen is going to be on the 6th column, 6th group, right? That means it wants to have 6 electrons to itself. If we look at this H2O molecule over here, oxygen will have 1, 2, 3, 4, 5, 6 electrons to itself, right? There's like 2 electrons in this bond right here, but 1 electron is going to belong to the oxygen, and the other electron is going to belong to the hydrogen. This is just saying that we're calculating formal charges here. But does that make sense so far? Right.
Yes.
Right. Because like this bond right here has 2 electrons, but it's shared because it's a covalent bond. We could say 1 electron belongs to the oxygen, the other electron belongs to the hydrogen right there. So if we calculate how many electrons the oxygen has to itself, it's gonna have 1, 2, 3, 4, 5, 6 electrons to itself. Right? And it wants 6 electrons because it's on the 6th group. So 6 minus 6 is 0. That's why it has a formal charge of 0. It's neutral. Right? Now, let me give you another one here where we have this oxygen right here. Describe to me how you would calculate the formal charge of this oxygen right here.
So I know I'm going to start with the number 6 because it has 6 valence electrons.
Mhm.
And then I'm going to see are how many it has right now. So it's 2. And then how much is shared with the hydrogens,
Mhm.
which is 3. And
Mhm.
then I would subtract that total. So that's 1, 2, 3, 4, 5.
Mhm.
And
Which
then that will get me a +1 charge.
yes. So this oxygen here would be a +1 charge right there, like that. Right? And at first, you might have to do these calculations, right, to get the formal charges. But as you do more practice, you're gonna notice a lot of patterns, and you could just assign the specific atom, the charge right away without doing the math, right?
Okay.
Because oxygen, like we're gonna see that it's gonna be neutral with 2 bonds and 2 pairs of electrons. It's gonna be positive with 3 bonds and 1 pair of electrons, but that's too much memorization, you know? So the best way to do is the math, and then over time you can memorize that with practice and repetition. Right.
Okay.
Okay. Now let's look at this over here. How would you determine the formal charge of this oxygen right here? Or if you already know, you can do it in your head and just tell me what the formal charge would be.
Would it be 0?
So let's walk through it. Describe to me how you got 0.
So I start with 6 because that's how many valence electrons it has. And
Correct.
then I count the number of lone electrons. So there's 1, 2, 3, 4, 5, 6. Oh, I missed one.
Mhm,
And then there's one that's being shared with a bond. So then I
mhm.
-7 and it's actually -1.
Yes, yes, yes. That's good. So you see how like talking through it slowly helps you figure out your mistake, and you could prevent that mistake from happening again in the future, like in the quiz or exam, something like that. Yeah, that's good.
Yeah.
Uh-huh. Okay, so now Levens, right? She can be sneaky. The lone pairs of electrons can be invisible, right? Like she doesn't have to draw out the lone pairs of electrons, but she does have to draw out the charge, right? So let's say, for example, we have something like this, right? Where we have this oxygen that is positively charged, but we see no pairs of electrons, right? They're invisible. How would you determine how many pairs of electrons this oxygen has right here?
So I know it starts with 6. So I
Mhm,
would consider that 3 of them are being bonded with
mhm,
like another. So then I would just subtract 3 and then get what and then divide that by 2.
mm, mm. So divide which number by 2? Sorry.
The remaining like
Mm.
after 6 minus 3?
Oh, 6 minus 3, 3 divided by 2. Oh, because are you thinking 2 because of the pair of electrons?
Yeah.
Okay, so we don't divide by 2. So here's what I did right here, how I got this equation. You know how when we calculate formal charge, we do 6, like whatever the oxygen wants based on the periodic table, minus like how many shared electrons it has from the bond, which is 3, because we see 3 here, 1, 2, 3. And then X right here is what we don't know, the hidden lone pairs of electrons that we do not see. Right? That's what we're trying to solve for.
Okay.
And it's gonna equal to the formal charge. And the formal charge is given to us, which is +1. Right? Because we see the plus charge right there. Now, how would you solve for X here if this was the equation?
So I move X to the other side and
Hmm.
then 1 to the other side and then I solve that.
Yep, that's good. So that means there's 2 lone electrons that we do not see. So we could draw that here. 1, 2. These 2 here were always there, but Levens can hide that from you from the quiz or exam. Right?
Okay.
And these 2 electrons right here are very important because they're gonna be the nucleophiles that are gonna attack something like that. Right? Like when we draw arrows, they always start from either a lone pair of electrons or a bond, and they go towards something that is like partial positive charge or fully positive charge. Like nucleophile attack electrophile, like that. Okay, and that's how it creates the
Okay.
bond. Okay, that's good. That's good. Now that's gonna be the same for nitrogen, and halogens like chlorine, bromine, fluorine, iodine. But you get the process ready, so that's good. Okay. So now let's move on to acid-base stuff, like how to determine what acid is stronger. Oh wait, yeah. Let's go back to here. Okay. So in Gen Chem, if this was a chemical reaction, the equilibrium constant is going to be the products, the concentration of products over the concentration of reactants. So it would be H3O plus concentration of A minus over the concentration of HA times the concentration of H2O. That's the equilibrium constant, right? Now, the acid dissociation constant is going to be the amount, the ability for the molecule to dissolve into protons, H plus ions in water, right? So water here is not going to be a factor, right? So the acid dissociation constant is going to be H3O plus times A minus over HA, okay? So let's say
And
HA
that's
has,
because water is neutral, right?
yeah, water. So water is neutral, and also no, it's not because of that. It's because HA is also neutral right here. The reason why we got rid of water is because we're now specifically focusing on the acid part of the reaction, right? What would you say is the acid, the HA or the H2O? What was the one that donated a proton, donated H plus ion?
The HA.
Yep, the HA. The HA here is the acid. So because this H2O here is not the acid, we're completely ignoring it now,
Okay.
right? The KEQ here includes everything in the reaction. Okay. And the HA will dissolve into the A minus ion, and the other H, like part of the HA, becomes the H3O plus right there, right? So one of the H's of the H3O plus was part of the HA, and the A minus is also part of the HA right there. Okay.
Okay.
But some acids are weak, some acids are strong. Weak acids will not be able to like dissolve into H plus ions, but strong acids will be able to like easily donate this H plus ion like that, right? So what do you think a strong acid will have? A high Ka value or a low Ka value? A strong acid that is willing to donate a proton.
A high Ka.
High Ka, right? Because a strong acid will have more of these A minus ions and more of these H2O plus ions, right? And if you have more of those on the numerator, then it's gonna have a high Ka value, right? So strong acid, high Ka value. Weak acid, meaning that we won't have as much H2O plus and A minus because it doesn't want to split up like that because it's a weak acid. We'll have a low Ka value because the numerator will be low. Okay. But we don't really use Ka values in organic chemistry. We use pKa values because Ka values can be like really big, like 10 to the 50, and those numbers are hard to work with. So the numbers that are easier to work with are going to be pKa values, right? So the Ka and pKa would represent like the strength of acid, but like it's opposite, right? Because pKa, the equation for that is going to be negative log of Ka, right? Which will inverse everything. A strong acid will have a low pKa value. A weak acid will have a high pKa value. That's because of this log right here. Like, if you take the negative log of a high number, you get a low number. If you take the negative log of a low number, you get a high number. Like that's math. We work with pKa more than Ka right there. But to explain pKa, I have to explain what Ka was first.
Okay.
Right? So the most important thing to remember here is, especially for leavens, because like she's gonna have you memorize pKa values, and that's what you would write in your note card for exams. A strong acid would have a low pKa value. Weak acid would have a high pKa value. So I'm gonna highlight that part because that's the most important part right there. Strong acid low pKa value. Weak acid, high pKa value. Okay. Okay. Okay, so let me explain to you some conceptual stuff here. Let's say that this HA is a strong acid. If it's a strong acid, would have a high or low pKa value?
It would have a low.
Yep, it will have a low pKa value. If it's a strong acid, it will have a high Ka value, but I didn't ask about Ka value. I asked about pKa value. So that means I have a low pKa value. And let's see why. If this is a strong acid, we're gonna get more of these ions here, meaning that when they form, they're gonna be stable. They're not gonna be reactive, right? Because they're gonna be happy and stable. They don't wanna like react with anything. They're not angry.
Okay.
Right? And I'll go over like what makes a molecule happy, what makes a molecule angry, but I'm just gonna explain the differences between strong acid and weak acid. Now, let's say this is a weak acid now. If this is a weak acid, we won't get as much A minus ions and H2O plus minus ions because once they form, this negative charge will be very angry, very unstable. So it's gonna be very reactive. It's gonna want to grab its hydrogen back and go back to what it was before, which is this HA weak acid right here. Right. Does that make sense? The difference between the strong acid and weak acid?
Yeah.
Okay. That's good. So now I'm gonna give you different examples here. The acronym that Fahrenheit uses for this quarter is ARIO, but when I learned it, I used cardio. Did Levens go over something similar?
Not that I remember. I kind of skimmed over that lecture.
Yeah, that's okay. I'm gonna go over this one because it includes more things. Cardio, dipole, induction. D and I goes together. Right. So let's start. Spelling out what this is. So C in cardio would be charge. A in cardio would be atom size. R in cardio would be resonance. D in cardio would be dipole. And I in cardio would be induction. Right. And then these go together. They basically mean the same thing. And O in cardio would be orbital. Right. And you can think of that as hybridization, like sp, sp2, sp3. Oh, hybridization. Okay. And they will usually go in order, right? So charge will have the highest priority and O will have the lowest priority. Let's go over this one by one. Let's start with charge. Okay. So charge. Let's say we have, and we're gonna compare acid strength here. Like I'm gonna give you two different acids, and then I want you to determine what's the stronger acid, right? Let's compare this acid versus this acid here. And I'm gonna underline one of the hydrogens as the acid. But there's something missing here. There's a formal charge missing here. What formal charge would this oxygen have right there?
You would do 6 minus 2 and then minus 3. And you would have 1.
Yes. +1 charge. How about this one? Does this what formal charge would this oxygen have over here?
That would be neutral.
It would be neutral because it would be 6 minus 1, 2, 3, 4, 5, 6. 6 minus 6 is 0, so it would be neutral. Now, let's say some random base, right? It doesn't matter. It could be like hydroxide ion or some other base like n-butyllithium, LDA, comes in and it's gonna most likely have a pair of electrons because bases will like be negatively charged and have a pair of electrons. Grab the hydrogen, make a bond with the hydrogen, right? So it's gonna form that bond right there. We're gonna break this bond right here between the hydrogen being grabbed and what it's attached to, those two electrons right there are going to go onto that oxygen right there, right? And then when that happens, we're going to get this right here, where this is the new pair of electrons, and this new pair of electrons came from this bond right here, right? Because that bond has two electrons, which came onto that oxygen right there. Now,
Yeah,
what charge does this oxygen have over here?
it's neutral.
Neutral, correct. And the base, because it gained a bond to hydrogen, it's going to be positively charged because it's going to be +1, right? It was neutral before, so it's going to be 0 + 1 is +1. But let's say this base here is negatively charged, which is going to be different, right? Let's say we grab this hydrogen right here. What do you think is going to happen now after we grab this hydrogen? Like, there's one more thing, arrow that we gotta draw.
The lone pairs will go to the oxygen.
The lone pairs of which bond? This bond or this bond? A or
The
B?
bond between B.
Yes, the bond between the hydrogen being grabbed and oxygen. Those two electrons right there are gonna go onto the oxygen. So because that's gonna happen, how many pairs of electrons would the new oxygen have? Right? Like, would this oxygen have as a result?
It would have 3 lone pairs.
Yes, it would have 3 lone pairs. So let's draw that out. But how many hydrogens would be attached to afterwards as a result?
Just 1.
Yes, 1, right? Because this one is taken by this base right here. So this oxygen with 1 hydrogen will have 1, 2, 3 pairs of electrons. So what would be the formal charge of this oxygen right here?
It would be -1.
-1, right? Did you do the math or did you just look at it and you already knew right away?
I saw that there were 6 lone pairs, so I
Mm-hmm.
know that, okay, that's gone. So I kind
Mm-hmm.
of did do the math.
That's good. Yeah, that's good. And that's good to start with, right? But over time, you're gonna see that we know this oxygen is negatively charged because that's 1 bond and 3 pairs of electrons, right? Like, over time, you're gonna get there. Like you could just look at it and know the charge right away without the math. But just keep doing it until you get there, right?
Okay.
Okay. Now, this base here that was negatively charged gained a bond to hydrogen. So what's -1 + 1?
0.
0. So it's gonna be neutral, right? So that's the difference between this base and this base. They both add 1 charge, right? +1. But because this base started as neutral, it's now positively charged. And because this base here started as -1 charge, it's now neutral. Okay, so there's gonna be different bases
Okay.
that you encounter, right? This is just a general thing. Okay. Okay, so now let's get back to the charge factor.
I have a quick question.
Yep.
So the hydrogen it carries an electron, so it gives it to the base. So is like the whole entire molecule neutral, or like just the base that you're talking about?
So this base right here,
Yeah.
this entire molecule is neutral. The base is neutral and the hydrogen is neutral. Because how many electrons does hydrogen want to be neutral? Like,
It needs a pair, like
it
with
needs a
another.
pair, right? Because how many energy shells does hydrogen have based on the periodic table? Like, where is it at on the periodic table?
It's in the start. There's
It's at the
1,
start, number 1, right? So how many electrons can the first energy shell hold in an
2.
atom? 2, correct. So hydrogen wants 2 electrons to be neutral. This hydrogen right here has 2 electrons, right, from that bond because it's sharing, right?
Mm-hmm.
1 electron to itself, 1 electron to the base, but because they're sharing, hydrogen has 2 electrons. And that because so if you do like the way we've been talking about, right? Oh, actually no, yeah, it still works because hydrogen is on the number 1, right? It has the number 1 group. It wants 1 electron to itself, so 1 - 1, 0. So hydrogen would be neutral and the base would be neutral as well.
Okay.
right? And this is just a general thing because you're gonna see that anything with a negative charge, when it gains a hydrogen bond, it's gonna be neutral. And let me give you a more concrete example for that. Right. Because let's say we use the same acid, H2O, but a base that will have negative charge is hydroxide ion. How many pairs of electrons does the hydroxide ion have? If you have OH and a negative charge, but the lone pairs of electrons are hiding from you. They're hidden.
It would have 2 lone pairs.
2 lone pairs? Okay, so let's try that. So there is a single bond right here between the oxygen and hydrogen. If there's 2 lone pairs right here and you calculate the formal charge, what would that be?
You do 6, it would be +1.
Positive 1. That is not negative 1, so that would be
So it would have 3.
yeah, because
Okay.
6 minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is -1, like that. Right? You could do the whole
Okay.
math again, where like if the lone pairs are not given to you, you could do 6 because that's how much it wants based on the periodic table, minus 1 because we see that there's a single bond between the oxygen and hydrogen, so we know there's 1 there, minus X because we don't know how many lone electrons it has, equals, we know the formal charge because it's given to us, -1. And then we just do the math to get X. Right, so that's gonna be 5 plus 1 is 6. So 6 equals X. So there's 6 lone electrons. 6 lone electrons. And I think this is where you got the divided by 2. Like 6 divided by 2 is 3. 3 lone pairs of electrons. 1, 2, 3. Right? But this X here represents lone electrons, not lone pairs of electrons. Right? Does that make sense?
Yeah.
Okay, good. Now, I'm just going to draw that out to show one of the pairs of electrons on oxygen is going to grab the hydrogen being grabbed by this oxygen and making that bond right there from this lone pair of electrons. This bond here is going to go onto the oxygen right there, giving that oxygen an extra pair of electrons, which is going to be negatively charged. And then the new oxygen, the hydroxide ion, now has 2 pairs of electrons, which are these 2, and 2 bonds. Does that make sense on how I got this?
Yeah.
Yeah, that's good. So what do you notice about this molecule and this molecule here? Like, what happened to the charge?
The charge, it went up.
Yeah, it went up. So whenever a base grabs a hydrogen, it goes up by +1. Right? We see that this overall base here was negative charge. When it grabbed the hydrogen, -1 + 1, neutral, 0, like that. This is a more specific example. I just gave it generally here when I first showed you it because you could use any kind of base. You could use this base as well if you wanted to.
Okay.
Yeah. Okay. Now let's go back to the charge here. We're gonna compare, let's say, this blue highlighted hydrogen to this pink highlighted hydrogen over here. Which one is more acidic? Which one has a lower pKa value? Right. And to do that, the very important thing for all of this here, right, is to compare the conjugate base stability. Okay. So if this is the acid right here, and this became this after the acid base reaction, after the proton transfer, right? Like let's say this is the acid. This would be the conjugate base. Does that sound familiar from Gen Chem?
Yeah, like, when the acid loses, the electron or H, it becomes into a conjugate base.
Correct. Which is this right here. Now, if this is the acid right here, what's the conjugate base? This, which we'll call A, or this, which we'll call B?
It would be A.
Yes, right, because this molecule here came from the acid. The conjugate base comes from the acid. Conjugate base. Okay, now let's compare which conjugate base is more stable. Let's call this A and let's call this B. Based on its structure and its charges, what looks more stable, A or B? Which conjugate base
A
looks more
looks more stable.
Yep, and why?
It's because the charge is neutral.
Yes, yes. And we want neutral charges in the molecule to be stable, right? And because this conjugate base is more stable than this one here, is it gonna be more or less reactive? Like, let's say this is a stable, happy guy. This is an angry, unstable guy. What's more reactive?
The angry one because it's negative, so it's gonna want more positive.
Yep, it's angry, very angry, so it doesn't like being in this state. It's gonna grab its hydrogen back and go backward to what it started with, right there,
Okay.
right? Whereas this one here, because it's very happy, it's gonna stay still. It's not gonna do anything. It's good, right? So that means that what
So
acid?
would you say in the second one, would you call that like a strong acid? Or would you just say like the base is stronger? That's why it can go reverse.
For the conjugate base here, because we know that it's more stable than this one right here, it's less reactive, less reactive. And if it's less reactive, do we consider that a strong or weak conjugate base?
Weak.
Weak conjugate base, right? Because strong acids give weak conjugate bases, right? Does that sound familiar in Gen
Okay.
Chem?
No, I don't remember
Yeah,
that
it's okay, it's
actually.
okay. Yeah, so you're gonna see that strong acids give conjugate base or leads to weak conjugate base, right? Strong acids leads to weak conjugate base. Weak acids lead to strong conjugate base. We
Okay.
see here that this is a stronger acid than this because it leads to a weak conjugate base, a less reactive conjugate base. Right? If it's a weak conjugate base, is it stable or unstable? This confuses a lot of students, right? If this,
But if it's stable.
yep, it's stable. It's stable, right? Because and then if it's stable, it's weak. It's not going to be reactive. It's happy to stay at the state. So that's why this acid here is able to give up its proton. It's able to donate that hydrogen like that.
Hmm.
Yeah. So what do you notice about the pattern here? If things are positively charged versus neutral charged, what's more acidic?
Um, I think the positively charged might be. I'm not
Yep.
sure.
Yep. The positive charge would be the one that's more acidic. Because it would be able to donate its proton and get rid of that to lead to a happy conjugate base, right?
Oh,
A weak
okay, yeah.
conjugate base. A happy conjugate base is a weak conjugate base. Whereas this acid here that is neutral is a weak acid because when it gets rid of its hydrogen, it leads to an angry conjugate base, which is a strong conjugate base,
Yeah.
reactive, right? Now, which one has a lower pKa value? A or B?
Um, I would say A has a lower pKa.
Yep, lower pKa value. And be careful how they word the question because what happens if I asked you instead, what has the lower Ka value?
Then it would be the other way around.
Yep. They're inversely related like that. A lot of things going on, right? Like a lot of relationships going on, like reactivity, stability, pKa, acid, conjugate base. Like there's a lot of things going on, right? Um,
Yeah.
but I hope like that explanation makes sense. Okay. Now let's move on to the next factor, which is atom size. Okay. So let's compare this acid to this acid over here. And let's just use a generic base with a negative charge. Good. It doesn't have to be negative, it can be neutral, but to make it more strong based, more reactive based, I'm just gonna put a negative charge right there. Okay. Can you describe to me the mechanism arrows on how this base would react with this acid over here?
Yeah, so the base, it would want to take the H. So the
Mm-hmm.
H would be taken by the base, which would lead to the base becoming neutral because
Mm-hmm.
the charges kind of cancel each other out.
Right. This base here grabs a hydrogen, which is this hydrogen over here. But there's something else that
Mhm.
has to happen when this hydrogen is being grabbed because
So
uh-huh.
with the hydrogen, that pair that you just highlighted between the O and the H,
Mhm.
both of those electrons, they go to the O and they become a lone pair.
Right. And what charge would that O have as a result?
Uh, the O would have um, you'd use a formula and then you do 6
Mm-hmm.
minus 2 and then uh minus 1. You would have 3 left.
Uh-huh. So you got the -2 because it came from this bond, right?
Yeah,
And you got the -1 because of this pre-existing bond that already was there before, right?
yeah.
But there are lone pairs of electrons here too. Like I didn't draw them out. That's the sneaky part about this question,
Okay.
right? So based
Would
on
the
yeah,
charge of that become negative? So you would you do 6 minus 2 minus 1 and then plus x equals to -1?
it would be so if you do 6, right? Oh, do you like if you calculate the formal charge, do you subtract or add the lone electrons that it has to itself? Right?
Subtract.
Subtract, right? So it wouldn't be plus x, it would be minus x,
Okay.
right? So
Okay.
how before we do that though, how many lone pairs of electrons does this oxygen have?
It has 2.
Mhm. Two lone pairs, correct. So I'm just gonna draw that there because it's already there, right? And I'm gonna draw another one. Do you know where this came from? This new one came from?
It came from the hydrogen.
The hydrogen here goes to the base, which is that hydrogen right there. It doesn't come from the hydrogen, it comes from
The bond.
the bond between the hydrogen being grabbed and the oxygen right there. Because this bond has 2 electrons, which gives this oxygen that new pair of electrons right there. Right.
So then
Uh,
what happened to the electron on the hydrogen?
The electrons on the hydrogen. So the hydrogens over here has 1 electron to itself, which is that 1 electron right there.
Hmm.
Right. But that 1 electron of the hydrogen alongside with the 1 electron of the oxygen is going away onto the oxygen right there, which is that right there. Right.
Okay.
But this base right here, let's say it has a pair of electrons because that negative charge is gonna have to come from somewhere, which is it's gonna have at least 1 pair of electrons. Right. This 1 pair of electrons right here is going towards the hydrogen, is grabbing that hydrogen, making that bond with that hydrogen right there. So if I highlight this pair of electrons in green right there, that's that green bond right there. The 2 electrons on this bond right here come from that pair of electrons on the base right there. I didn't draw that out, but it's there,
Okay.
right? Does that make sense?
Yeah.
Yep. And I could also highlight this bond here that was there right there in pink, which is going to be this pink lone pair of electrons right there. Okay.
Okay.
Yep. Now, what charge would this oxygen have right here? Now we know all of the lone pairs of electrons and single bond or like bonds it has.
It would be -1.
Yeah, -1. Correct. Okay. Now let's do the same for this over here. It's gonna grab the H, the bond between the H being grabbed and whatever atom it is, in this case it's sulfur, is gonna go into the sulfur. And how many electrons would sulfur want based on the periodic table? Like, yeah, have
Is
the
it
periodic
in the 5th column?
it's gonna be on the sixth column as well,
Okay.
right? Because on the periodic table, oxygen is right there and a sulfur is right below it on the periodic table,
Okay.
right? And because of that, well, how many pairs of electrons would sulfur have? Like before all of this, how many pairs of electrons does sulfur have?
It has 6.
It wants 6 electrons to itself. So that means it's very similar to oxygen, right? And if it's neutral, it's gonna have 2 pairs of electrons. 1, 2, right? Because if you do 6 minus 1, 2, 3, 4, 5, 6, 6 minus 6 is 0, neutral charge. Does that make sense why this sulfur has 2 pairs of electrons?
Yeah.
Yeah. If you didn't know that, you could do the math, right? Like 6 minus 2, which is coming from these 2 bonds, minus x, because we don't know what that is, equals 0. And if you solve for x, that's going to be 4 equals x. There's 4 lone electrons. 4 divided by 2 is 2. 2 lone pairs, like that. Okay. Now, it's going to have similar thing. Okay. Now we're gonna do the same thing. We're gonna do the same thing to determine what's the stronger acid, this or this. I want you to tell me how you would do that. And it's okay if you get stuck, just let me know.
Okay. To determine what's the stronger acid, I know we talked about like the stronger acids will have a weak conjugate base, and then they
Mm-hmm.
both are like the same charge. So I would say that they're both the same.
Yep. They both have the same charge on the conjugate base, because this is the conjugate base, Cb. This is also the conjugate base, Cb. And they both have negative charges. So that's why we are not looking at the charge factor now, because that's irrelevant, because they have the same charge. The next factor we look at is atom size, right? And negative charges, they want to roam around, they want to breathe a lot, right? They want to move a lot, and they're going to be able to move a lot on a bigger atom. So on a periodic table, do you remember the trend of atom size? Like if sulfur is below oxygen, what's the bigger atom size?
Um, Sulfur has more protons,
It has more
but the
protons.
same amount of shells, so is it smaller?
Sulfur is going to be bigger, right? Because it's gonna have more shells, right? Because it has more protons, it's gonna have more electrons. And then you know how if an atom has more, if an element has more like electrons, it's gonna fill up the energy rings like higher and higher,
Yeah.
right? Because sulfur has more energy shells, sulfur is gonna be bigger than oxygen. Because let's say like this is the periodic table right here. Atom size is gonna increase as you go down the periodic table. Right. Because as you go
Okay.
down the periodic table, will you be increasing electrons or decreasing electrons?
You'll be increasing.
And if you're increasing electrons, would you have more or less energy shells?
More.
Yeah, more. And if you have more energy shells, would you be bigger or smaller?
Bigger.
Bigger, right. So now, because sulfur is bigger than oxygen, the electrons have more space to move around to breathe on sulfur, right? So because sulfur, like this conjugate base here is more stable, now which was the stronger base? I mean, stronger acid. A or B? What's the stronger acid if this conjugate base here is more
B,
stable?
because it's bigger atom.
Yeah, B. To look for the stronger acid, look for the more stable conjugate base or the weaker conjugate base, which is this right here. It's good. You got it. Okay. So uh charge is not always the factor, right? Because we saw here that they had the same charge, negative charge, so we don't look at that anymore. The next thing we look at is atom size, which that determined what was the stronger acid, right? Like all of these right here will determine what's the stronger acid right there. Okay.
Okay.
Okay, that's good. Am I going too fast, or is it a good speed? You want me to slow down, or
It's a good speed. Would you say the sulfur conjugate base is more stable? Like why would you say it's more stable?
yep, I would say it's more stable because of the atom size, right? The charge is the same as this, both negative charges, so we don't care about charge anymore. But now we move on to atom size. We see that sulfur is bigger than oxygen, meaning that there's more space for the electrons here to move around, to breathe,
Oh, okay, okay.
right? Oxygen is smaller, so there's less space for these electrons to breathe, to move around.
Okay, yeah, that makes sense.
That's good. And that's why this is more stable conjugate base. More stable conjugate base equals weaker conjugate base, which equals it came from a stronger acid, right? And then if it's a
Okay.
stronger acid, would this have a higher or lower pKa?
it would have a lower
Yeah,
pKa.
yeah, right. Yeah, it took a while to get there, because there's a lot of like relationships that we had to connect together. But I hope that connection is like getting more clear now. Right,
Yeah.
that's good. Okay, the next factor we're gonna look at is resonance. Have you learned about resonance yet? Have you practiced with that
Um, I think we briefly went over that in discussion
in
yesterday.
discussion? Okay, resonance, aka delocalization, is gonna be the movement of electrons, right? So we really need to understand resonance before we move on to this factor, but I'm going to give you a simple example of resonance, and then we could do more resonance practice in our next session. And you know how I invited you to like the school, right? And you're in that
Hmm.
platform. I will also have like office hours, and if you can make it at that time, I could go over more practice during those times as well. And there's gonna be an exam one review
Okay.
session. Wait, but for Levin's 118A, she doesn't do midterms, right? She does bi-weekly quizzes.
Yeah, yeah. 5 quizzes.
Bi-weekly quizzes. Okay, yeah, that's different than Levin's 118C class this quarter because she's doing midterms for their class for 118C. Okay, that's good to know. Good to know. Okay. Um, let's say we are gonna compare this acid with this acid right here, and it's just a generic base. Okay. Now we already know how this base is gonna grab the proton, which is this H right here, which is gonna be from this arrow. But this arrow is coming from the base, which means that this base will have at least one pair of electrons like that, right? To make a bond between the base and hydrogen. So this bond right here, which has 2 electrons, is going to go to the oxygen. Okay. And if you calculate how many lone pairs of electrons does oxygen have, it will have 2 lone pairs of electrons because it's neutral. If you draw out the conjugate base of that, it's going to look like this with a negative charge. And the base is going to be neutral with the proton it grabbed. Let's do the same for this one over here. The oxygen over here will have a negative charge because before it had 2 pairs of electrons, now it has 3. And then 1 bond, right? And the base is going to be neutral. Okay. Now we see that this is the conjugate base of the first reaction. This is the conjugate base of the second reaction.
Hmm.
We see that they have the same charge. They're both negatively charged. Negative charge here, negative charge here. So we don't care about that. We see that they're the same atom, right? Where the charge is at, oxygen and oxygen. So because they're the same atom, they have the same size. So we don't care about atom size as well. Then we move on to resonance. Which one, based on looking at it, do you see has resonance?
Um, would it be the first one?
Yep, it will be the first one, right? Because we see that this carbon here, what is the hybridization of that carbon? SP, sp2, or sp3?
It would be sp2.
Yes, sp2. And if it's sp2, how many unhybridized p orbitals does it have?
2.
It will have so if it's sp2, right? Because sp3, like let's say we have 1s and 3 p orbitals. To get sp3, you're gonna combine or hybridize all 4 orbitals to get sp3, right?
Okay.
So it has 0 unhybridized p orbitals. But if you have sp2, we're gonna combine these 3 orbitals to get sp2, meaning that we have 3 sp2 orbitals and only 1 unhybridized p orbital right there. Right. So this might not make a lot of sense right now because we didn't go over resonance, which we can go over next week. But I'm just gonna draw out the resonance arrows here in pink. One of the pairs of electrons on oxygen here is gonna go down to create an extra bond right here between this carbon and oxygen, right? But that's gonna break the octet row of this carbon because that carbon is now gonna have 5 bonds. 1, 2, 3, 4, 5. To conserve the octet row, I'm gonna move one of the bonds here to this oxygen right there, which has 2 pairs of electrons. And when we draw the resonance structure, we have to draw this double-headed arrow to show the resonance structure. which is gonna look like this, and this oxygen here is gonna be there, negative charge right there. I know I went kind of quick on that, but like if you have any questions, we could go over this topic next week, resonance. But yeah, any questions on this, Tanaya? Like how I got this resonance structure here, like the movement of these electrons to get the structure here.
No.
Okay, that's good. Now, this oxygen here cannot do resonance because the atom nearby that has two invisible hydrogens here, that atom is sp3 hybridized. Resonance cannot happen with sp3 carbons. It can only happen with sp2 atoms or
Okay.
sp atoms, right? So that means that this negative charge here is stuck. It's trapped. Whereas this negative charge here is able to move. It's delocalized. It's able to breathe. Like this negative charge here it moved to the other oxygen right there. And because of that, what do you think is more stable? Conjugate base A or conjugate base B?
I would say A is more stable.
Yeah, more stable because it has more resonance, more delocalization. Right.
Okay.
Right. And now final question. If this conjugate base is more stable, what's the stronger acid? This or this? A or B?
A.
Yep. Meaning that it will have a lower pKa value because that's what Leibniz will worry about. Well, she will also ask about Ka values because this is 118A. So if it has a lower pKa value, it will have a higher Ka value. If this has a higher pKa value, it will have a low Ka value like that. So just keep those relationships in mind for the exams. Yep.
Okay.
Yep. We could go over the rest in office hours next week or our session, but I hope that helps. And if you have any questions, just send me on Discord and we could go over those as well on our sessions as well.
All
Yeah.
right. Thank you so much.
Of course. Thanks for creating that Discord again for me. I really appreciate that.
Yeah, no problem. I've made it like an about section so you can post about your services and everything in there.
Oh yes, yes, yes. I'll do that soon. Sometime this weekend. Yeah.
Okay.
Yeah. And I'll post the session notes and record it to your folder that I shared with you, so you could review it anytime you want.
Okay. All right. Yeah, thank you. I appreciate it. Yeah, you teach
Yeah.
pretty good. I'll tell my friends about you.
Okay. Okay. Thank you. Thank you about that. Yeah. Okay. Have a nice day,
All right.
Tanaya.
Have a good day.